off and go over some lesson stuff, go through a bit of the playground. We'll be talking about the motivation for binary search, talking about a new type of time complexity, which is logarithmic time. We'll talk about what that means, why we're going to see that in different functions, and it's a big part of how we think about algorithms moving forwards, especially as we start getting into search algorithms, which we'll do in the next couple weeks. We'll implement binary search, so go over what is this thing that we're building, how can we use it, talk about a couple implementations where you might find it, and then there is an associated lab that has some questions that are asking you to either implement binary search or use it to solve a variety of questions. So that's in terms of structure, so let's get right into it. Binary search, what is it, what are we talking about? We have found things before when we're looking for them. It's a good place to start. When you wanted to find something, let's say you have an array of elements called, is this big enough or should it be one tick bigger?
Bigger.
Bigger? Good. I think there's a presentation large. Is that a new preference? So exciting. All right. So let's say that we have some array of names, and we want to find one of them. We've got Abe, we've got Bart, we've got Carl, we've got, sure, Lenny. All right, so let's say we've got a bunch of names and we want to find if one of them is here. How have you written code to find if a given name is in this list so far? Contains, right? So you've written here something like if names dot contains whatever. Homer, then print so there's supposed to be an apostrophe? Nice. All right, so this is how we've been writing search code so far, right? Now, we're using the built-in contains that comes with an array, but because we like talking about time complexity, how long do we think that this contains is going to take us to find something? Linear. And why linear? Yeah, because we have to iterate through the array, right? And we find things by looking one at a time. And to kind of prove that, we can write our own contains method to see what is it doing, and it's really not doing anything more than this. So this is what a contains method looks like here. We're going to make our contains like Swift, so our contains is also going to work on any generic type that conforms to comparable. Then our contains is going to take inside of it some array of type T and some target, or type array of T, and some target of type T, and we'll return a bool. So this is our function signature that it's using as well to some degree for what containment looks like. Now, what is it doing? Well, pretty much the thing that we just said, right? We're saying, in order to find if something's there, we're going to iterate through everything. So for every element in the array, if the element is equal to the target, return true. And if it's not, return false. Hopefully this doesn't look too shocking or scandalizing. This is just a clean and simple way to be iterating through and finding if an element is there. If you wanted to be fancy, you could also do it in a one-liner. Do something like return, like you could filter and to make sure that it has that element, or something like filter, like $0 is equal to target, and then return that it's not empty or something. This does the same thing, basically. So like, it's not super pertinent to this, but just get used to being able to play around with higher ordered functions a little bit as solving what kind of problems you want to solve. But for now, we don't need to worry too much about this. And instead, we can look at the more straightforward implementation. It's also just a side note on this. This isn't better code than this code. Good code is code that people can read. And if it's harder to read this, then it might not be good code. So it really depends on what you're writing for. I really like code that's just very clear and expressive about what you're trying to do. So there's no problem writing out things more like long form like this here. Okay, now we can test to see how long does it take us to find something in this. So we're just going to make a number of operations variable here. And every time we look at an element, we're going to increment it. Then, if we find it, we'll go ahead and print found target in number of operations. And if we didn't find it, we'll go ahead and print that we didn't find no target, or didn't find target in whatever operations. So this is going to help us do a little bit of benchmarking, just so we can A, prove out that we are in fact looking at everything, and B, try to figure out what the motivation is maybe there's a better way that we could be looking. And that's going to be the punchline, is how can we find a better way to be looking here? So I'll scrap this for now. So for our contains here, if we're going through our array here of names, we can do contains, names, target, Homer. And this will go ahead and run through this array and tell us whether or not it found Homer inside our names here and how many operations it took. So we see that it's false. We didn't find it in 4 operations, and we only have 4 things in our array. So that makes sense, right? If we don't have it, we don't know where the thing is. It could be right at the end. So we have to look at everything until we find it. Now, we'll notice that for this array, it's ordered in a very particular way as I created it here, right? How is this ordered here? Yeah, how is the array ordered? It's alphabetical, right? Or if you want to be fancy, it's in lexicographical order, which is a fancy way of saying alphabetical. It's alphabetical, but it cares about like the next character and whatnot. But yeah, it's alphabetical, right? It's in order from smallest to greatest. Now, if you knew that your array was sorted in order from smallest to greatest, then we don't necessarily need to look at every element to the end to find what we're looking for. So in this example here, right, if we're looking for Homer, right, or let's imagine that our array didn't have Abe in it, instead had Homer. Let's mix up our array, like so. So let's say our array looks like this, right? If I want to know if this array has Abe in it, do we think it could be at the end if I tell you that the array is sorted? So if you knew that this array is sorted, right, where would you look for Abe? At the beginning, right? Because you're like, well, it's sorted, and I know that the A's are at the beginning, so that's where I'm going to look. You wouldn't even need to look at the end. So if it's sorted, we can begin to see that there might be something more clever we can do instead of looking at everything one at a time. Because we know generally where things are. We know that if we're looking for Abe, but we've already seen Carl in the middle somewhere, we know Abe can't be to the right because this thing is sorted, someone has guaranteed to us. If the array wasn't sorted, all bets are off, and we have to just go through one at a time. So what strategy can we use to come up with the most efficient way of finding a name in a sorted list? So imagine like a phone book, right? So you're looking for a name in a phone book. You could start at page 1, and let's say you're looking for, Homer Simpson in your phone book. You could start at page 1, all the names, last names ending in A, and go through page 1 and look at, Aaron and Aronson and whatever other names that end in A, and then go on to page 2 and look at a bunch of B's. But you might be wasting more time, because there might be like 500 pages of A's before you get to anything else. So what might you do if you were looking in a phone book for a name? Yeah?
You would open it in the middle and you'd say it's the first name beyond what you're looking for. If it is, then you split the first half again, you look through that, you say it's before here. Or if it is, you split that again and look at the front half. If not, you go into the second half and you go from there. Exactly.
So what we can do is we can take advantage of the fact that, now, the reason why we start in the middle is we don't necessarily know how the names are distributed, right? Because in the US, maybe we know it's sorted, but we don't know that it's evenly distributed. So, but starting in the middle is as good a place as ever, right? Because we can then take our list here, our list of names in our phone book, we start in the middle, and we say, is the name that we're looking for, was it the front half or the back half? And because we know our list is sorted, we can then say, oh, we're looking for Abe, let's say, and the name that I found was Lenny. we say, oh, well, Abe comes before Lenny, so we get to chop off this entire back half, and we never touch it. Now we're just going to look at this array here, and keep going through that process until we either find it, or find where it would be if it was there, right? Find the two people would be between, and then say like, well, we found Aaron, and we found Anand or something, and Abe wasn't in between them, so we know that it's not there. So that's going to be our general approach to something that's, given our list is sorted, faster and a little more efficient about finding something that we're looking for. So how much more efficient is a reasonable question. So before we actually go into implementing, like, how do we build this, let's talk a little more about like how we can actually devise the efficiency of an algorithm like this here. And also, if you've ever, it's the same type of thing, if you've ever played like a guessing game with someone, like I'm thinking of a number, like, you know, between 1 and 100, and it's like 12, and you're like too low. Your next guess probably isn't going to be 13, right? You want to kind of split the difference and come up with a better strategy there. So let's find out what that splitting does for us here. Let's imagine that we have an array of, let's say, I don't know, a bunch of elements in it here. 4, 9, 10, 12, 15, 16, 19. Okay, let's got a bunch of elements in our array, right? If we were to search, how many do we actually have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sure. So let's say we've got 10 elements here, right? If we were to search this manually, like we do with regular arrays, we don't know that they're sorted, it would take us 10 operations to guarantee that we've either found it or didn't. Yeah. Okay. So what do we want? So what about our better way where we flip to the middle of this kind of phone book of numbers and check that out? So let's flip to the middle. Our middle here is we've got 0, 1, 2, 3, 4, 5, 6, 7, 8. Is it 9? I count? No. Index 9, right? So the middle is going to be in between these two, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's pick 5 then. 1, 2, 3, 4, 5. So this guy right here. So this is not in the exact middle, right? Because we've got these here, so we can kind of choose how we're doing with our algorithm. Let's just go a little bit lower since that's what we did before. So we'll look for this 10 here, right? Let's say also that we're looking for 2 as a target. That's what we're trying to find. Now again, it would take 10 operations to do a containment to see if it was there. It happens to be missing, but this algorithm for contains isn't smart enough to know that our list is sorted, so it's going to go all the way to the end, and it's going to be trying to look for 2 over here, even though we know that it would have passed it. Our algorithm will be smarter. Say our target is 2, and we start here. We say, well, 10, that's too high, so the number we're looking for has to be here. So we do the same process. We then say, oh, let's look in the middle of these. This 3, let's say. We say, that's still too high. Let's look at this value here. There's only one thing left that we haven't looked at, and it's not our target, so we know that it's not there. So we only had to look at 3 things in order to find out that that 2 wasn't there. That's a lot faster than the other algorithm. So if we have an array, our .count, or n, with 10 elements in it, in this case here, we only have to look at 3 elements to know whether or not our thing was there or not. And that's pretty much the maximum number of splits we can do, right? For any other number that you give me, it won't take more than 3 operations to find it. Right? Let's say that we had given like 18 instead, right? If we're trying to find 18, we start here, go to the middle here. This is still too low, so we split between these. We find 19, and then we see that there's nothing in between these. So we've also done it in 3 operations. So no matter what we're looking for in this range, it's not going to take more than those 3 operations to find it. Now, what if instead we had, I don't know, say 16 things inside of our array? If we had an array with 16 things, 2, 3, 4, 5, 6, 6, 7, 8, So if we have an array with 16 things, and we want to find out if something's there or not there, we're going to run through the same process. We start midway through. Then let's say that our target is 3. Why not? We know that 3 is on the back half of this. So we cut again. We go here. We cut into these, and we'll end up looking here. And now we know it's in between, and we'll look here, and that is the value we're looking for, and then we're done. That was 4 moves to find it. And in fact, this is the same with 10 elements as it is for 8. If 10 can find it in 3, 8 can also find it in 3. So if we have 16 elements, by cutting these repeated halves, we end up only needing 4 operations to find if it's there. Let's try one smaller. Probably should have started there. That's okay. So operations. So let's say instead we had an array with 4 elements in it. We have 1, 2, 3, and 4. The worst case is that we'll cut in half here, so we'll go like 1, 2. We either have it or we don't, basically, like from that division there. And if we have 2, or I suppose it's kind of 1 greater than that, but in general, that's the gist of it. So if there's 2 elements, we just look at one of them, see if that's the one that we're looking for. Again, there's a little off by 1 factor in this, because if there's 2 elements, you do need to look at both of them. So it's kind of fudged, but that's a basic idea. If we then jump up and say, well, how many do we need for 5 operations to be true? Because we still had a bunch of breathing room down here for a bunch more elements we can make and still do those cuts. And it turns out that in order to go up to 5 operations, a requirement that you might need to do 5 operations, we'll need to have 32 elements to look for. And if we have an array with 64 elements in it, this algorithm will get it to us in only 6 operations. That is a lot faster than our going through one at a time and trying to find out if it's there or not. And the reason for that is because we get to keep taking that array and chopping it in half repeatedly. So say for this, when we have 64 elements, we look at one thing, and then we end up with 32 elements. Then we look at one thing, and now we have only 16 elements. We look at a thing again, and now we cut, and we only have 8 elements. We split it in half, now we have 4 elements, and half again is 2, and then half again gives us back to that 1. Because we keep chopping in half every time, we get to decrease pretty rapidly. So we can see from this, if we started with 128 elements, that first chop in half will reduce us back to this state. So this grows very slowly, which is a really good thing from a runtime perspective. Because we could have 128 elements inside our array, and we could know if something was there by only looking at 7 of them. That's really efficient. That's a really good algorithm. If you're able to write algorithms that are that fast, you're going to make it a lot faster to be writing the kind of code that you want to for systems that care about such things. Now the question is, how do we describe this relationship mathematically? So before, when we had just containment, it was a pretty clear one-to-one mapping, right? If we had 10 elements, it would take us 10 operations to find, and that mapping we called O of n. Because you say, give me the number of elements, and the number of operations is the same, a one-to-one map. For this relationship, it looks a little bit different, right? Now, depending on your mathematical background or knowledge, like, do we see a relationship between the numbers on the left? Do we know how we would describe that? Yeah. Yeah, so on the left side, we see powers of 2, right? So we definitely need to be thinking about the like exponential power space for like how we're growing, right? But growing exponentially would mean that our operations were increasing Instead, it's the inverse of that. As our array gets bigger and bigger and bigger, our operations increase really, really slowly. So now the question becomes, if this was flipped, right, we'd say, oh, 2 to this power is 8. 2 to this power is 16. 2 to the 5th is 32. But what's the opposite from that? Yeah, so that's a logarithm. Now, the only thing we really need to know about logarithms for now is logarithms undo exponents and represent dividing a log. That's conceptually what they are. So in this case here, to get to this relationship, for example, our question is, we've got 32, we have to end up with 5, and we have some question mark thing right here that gets us from point A to point B. So we're done the other way. Let's say 2 to the 5th is equal to 32, right? So if you're unfamiliar, exponentiation, this here means 2 multiplied by itself 5 times, which is the same represented here. The way to undo exponents, just like we can undo addition with subtraction, we can undo multiplication with division, we can undo exponents with what are called logarithms. A log is something that undoes an exponent, and here, just like this represents 2 multiplied by itself 5 times, this represents 32 divided by itself enough to get down to where we're trying to go. So 32 divided by 2 a bunch of times until we get back down to 1. So we take this 32, and we say, how many times do we need to divide by 2 before we end back down to 1? So we say 32 divided by 2 is 16, then to 8, then to 4, then to 2, and then to 1. So we had to divide by 2, 1, 2, 3, 4, 5 times before we get back down to 1. So that's what logarithms do. They say, how many times do we have to divide this by this before we get down to 1? Exponents say, if we just multiply this by itself this many times, what do we get? Logarithms are undoing that kind of operation. So this kind of growth, where we see the n, or the count of the array, increasing really, really quickly, but the number of operations increasing really, really slowly, is called logarithm time, logarithmic time. And this is represented by what you see as log base 2 of n. But, and here's the kicker, in computer science, because we're so frequently dealing with powers of 2, people just ignore this 2 entirely, and they just write log. From your math classes, log would always generally mean log base 10. In computer science, log means log base 2. That's a fun fact that no one tells you until you are getting confused by things. So, and that's because we care about powers of 2 a lot and doing that repeated division by 2 to get down to a number. Yeah?
Can you repeat what you said logarithmic time was in this case is when the y-x increases?
The number of, the size of the array is increasing exponentially, but the operations are increasing linearly. So the array gets really big really quickly, or put the other way, with the same number, as the array gets really, really big, it doesn't take that much more work to find what we're looking for still. So if you're working linearly, as the array gets bigger, you have to do an equal amount of work to catch up with it. For quadratic stuff, if the array gets bigger, you have to do more work to catch up with it. For logarithmic, as the array gets bigger, you have to do less work to catch up with it relative to how it's growing. Yeah?
And you said that Swift.contains does this?
So Swift contains does a linear algorithm. What we wrote right here, this is what Swift is doing. Pretty much word for word. It does not do this for you, and the reason is it doesn't know if the array is sorted or not, right? In order to find out if an array is sorted, you actually need to go look at everything, right? Because if you want to know if an array is in the correct order, you actually have to start at the beginning, go through it, and see if the next thing is bigger than the previous thing. So if Swift tried to build this in, it could, but it would get rid of all of the gains anyway, since they'd have to go through the array just to see if it was sorted or not. So what we're going to implement is our own algorithm that says, given a sorted array, we're going to make an algorithm that finds an element in as few operations as possible. And the algorithm that we're going to write is going to run in logarithmic time. It's going to run based off of log base 2 of the number of things in the original input array. Okay, so let's go ahead and see what that might look like. So to start off, let's think about the strategy we're going to employ when writing this. So hopefully we understand the gist of what our algorithm should be doing. Take a sorted array, look at the middle, see if the number we're looking for, or whatever we're looking for, is smaller or bigger than it. Ignore everything in the other half, and then do this again in the half that we care about. Whenever you have a structure for a problem that's explained like that, right, it's just check the middle, get rid of half, get the new middle, and then do it again, and just repeat that. That sounds like a lead-in for a recursive algorithm. Now, anything you can do recursively can do iteratively. But in the way I explained this process, the real core algorithm of it is check the middle, chop off half, do it again with the other half. That's a good candidate for writing a recursive algorithm. Because we can get the explanatory stuff of the process we're going through, instead of having to manually track a bunch of indices and doing it that way. So, let's see what this starts to look like. So we are going to write our binary search method, which is going to take in a comparable thing. It's going to take in the same stuff as before, and some target, and return a bool. Now, we're writing a recursive method. So we need to think, like we do recursively, there are two things we need in a recursive function. Those are base case and recursive call. So now we need to start thinking about how we want to be chopping this up and solving our problem from there. Now, we could do it relative to the array, so we keep passing in different smaller arrays each time. Or we could do it by tracking the search range of the different indices that we're working with. We're actually going to go with the second one, the reason being, if we give this thing a new array every time, because Swift is a structs are passed by value, we'd have to be building these new arrays every time, which would make it slightly worse from space complexity. So we're going to add in a range here that's going to represent the range that we're searching for. Now, there's something a little bit fancier. We don't want to have users of our API pass this in when they're starting, right? We don't want them to write binary search array target and put the ranges, because we know what it is when it starts. So we're going to set this to nil initially. And the idea is, if they didn't set it, the user shouldn't call with that. And if they didn't set it, we're just going to use the full range of the array. Okay, and of course this then has to be optional. So let's do that little bit of groundwork boilerplate stuff first, where we're going to establish, I'll just return here so it doesn't yell at us. We're going to establish the range is either whatever they put in, or whatever we put in when we're calling this, or the full range of the array the first time that it's called. So we're going to go ahead and make something new called search range, which is going to be a non-optional range of integers. Then, if they gave us a range, so range is range, we'll go ahead and just use theirs. Search range equals range. And if they didn't supply a range, then we'll go ahead and assign the search range to be the range of the entire array. You haven't seen end index before. End index is one past the end, so you do a open range up to it. Convention. Okay, so now we've got the range that we're looking at. Now we need to say, when are we done searching? There are two conditions that we're done searching, and it's either we found it, that's a good one, or the range that we've got back for us is a range that overlaps with itself. So the way that we'll be splitting it up is to say, let's start with a range that goes from 0 to 9 as a range. We're going to then chop in half one way or the other. Let's say then we go from 4 to 9 as the next range. We chop again. We go from 4 to 7, 6, whatever it is. We chop again. We end up with 4 to 5. And if our next chop would take us to the same element, or would take us to 3, then we know that we haven't found it. Because we've looked at everything, and now we're trying to build a range that doesn't make sense anymore. So our first base case is going to be if the search range's lower bound, which is just the number at the bottom, is greater than or equal to the search range's upper bound, then we return false, because we didn't find it. So that's going to be our base case for if there's nothing in the array, eventually what's going to happen is that our ranges here are going to overlap. We're going to end up building a range that doesn't make sense anymore because we've looked at everything. So now we can get into the meat of our recursive call here. We could put this inside an else if we want to. Doesn't really matter, it'll get executed anyways. So inside a recursive call, we want to then be finding out first, what is that middle index of the range that's been given to us? So we're going to make this middle index, and we want it to be in between the lower bound and the upper bound. Now, if the lower bound is 0, we just take their average, add these up, and divide by 2. If it's not 0, if we add up 4 and 9 and divide by 2, we don't necessarily end up in the middle of what we're looking for here. Yep. We'll find out. So it does sound like it's X in the middle. Well, let's find out. So let's start off with our middle index. So we're going to take that lower bound. So the search range's lower bound plus the search range's upper bound, and divide those by 2. I did something else before. So I'm going to do some live debugging for a second here. Is this always the middle index of a range that we have? So let's say that we have a range that goes from, say, 4 to 9, right? Yeah, that sounds like it. I don't know why we did something else before. That could be fun. So we go from 4 to 9. We add up 4 and 9, we get 13. We divide 13 by 2 using integer division, and we end up with 6. This sounds kind of reasonable, right? I'll start with this, and we'll debug it if it gives us some problems.
Integer division just drops the remainder.
Yeah, integer division drops the remainder, exactly. So now we found the middle index. I do think this is wrong, by the way. I did something different before. I don't know why I did it. Oh, I think this is the same. Oh, this is different. Let's do some live debugging here. How are these different from each other? This is what I did before. Correct middle index. True. Let's see. Let's take some numbers here. So let's say that we had a range spreading from 5 to 20. Let's say the middle index with this one here would be 5 plus 20, which is 25, divided by 2, which is 12. So this would be 12 under that scheme. And this one here would be 5 plus 15 divided by 2. 15 divided by 2 is 7. And then 7 plus 5 is also 12. Are these things equal to each other? Yeah, I think these are going to be the same, right? Maybe not, that'd be fun. Mm-hmm. Yeah, are these, let's just do some algebra. Okay, algebra time. All right. So we have, let's find the difference between those. Let's say the lower bound is L and the upper bound is U. So we have L plus U over 2. And the thing that we're comparing that against is lower bound plus, lower bound plus the upper bound minus the lower bound, this expression over 2. Right? And we want to see what the difference is between these two expressions. Man, algebra, right? Alright, so let's go ahead and combine these terms here. So we'll take, this L will represent as 2L over 2 plus U minus L over 2. Now we can add fractions. So we've got 2L plus U minus L over 2, which is equal to L plus U. Great. Algebraic proofs. So these two are in fact the same, demonstrated by our proof up there. So good. I didn't know that, so now I know that. I was wondering why they were different before. If you do see things like that, it's good to kind of like do a gut check. This was obviously quite live, but do a gut check and say, do we end up with like an off by 1 error here? Is it like trying to cut off some number? And it turns out that this is just a longer way of writing what we wrote out here. So let's go with the one that seems shorter. All right, that was a fun algebraic interlude. Brings us back to some math, right? So what we're doing now that we found our middle index is we want to be finding the element at that middle index, and then compare that with our target. So we're going to do the happy one first. If the target is equal to the middle index, then we're good to go. Return true. We found it, right? Or not the middle index, excuse me. The array at the middle index. So if the target is equal to that value that we were searching for, we found it, we returned true, we're done. No recursion. If that's not the case, and instead we have to look at either the back or the front half, then we have to figure out what does that look like. So if instead the target is less than the array at the middle index, or the value at the middle index, if, then we need to figure out, well, the target was smaller than the middle. We're ending up in this case, too much algebra. We're ending up in this case here where the target's 2, and the thing we're looking at was 8. So we need to check out this array. So we need to build a new range that goes from the beginning of our range, because we don't know what the lower bound is yet, up to, but not including, the thing that we just looked at. And we need to run this same function again on that range. So we're going to do that right here and say that we're going to run middle index. We're then going to return, true or false, whether or not this array going from this target, same array, same target, but the thing that's different is our range is instead of the whole range of the array, we know that we don't need to look at anything that's bigger than this value that we found. Because we're looking for a target that's smaller than it. So we don't need to look at any of this range. So we get to pass in a range that only checks the front half of what we've seen so far. So this range is going to go from the search range's lower bound up to, but not including, the middle index. If we went up to and including the middle index, then we might end up checking the same thing infinitely. So this is saying we're still going to run this search, same function that we're running here, except it's going to be searching a smaller part of the array because we know that everything from middle index to the end doesn't have it in it because we are assuming that the array is sorted. Okay. In the other case, now there's the fundamental theorem of algebra, I want to say, is that for any two values, they're either equal, one is bigger, or one is smaller. So that's why we just get to write else here, because those are the only three cases that we can have. This case means that we were looking for a number that's bigger than our target. We want to do the same thing, but instead of picking a range that goes from here to here, we want to build a range that goes from here to the end. So we're going to do that by returning our binary search. We're going to have the same array, the same target, still looking for the same thing, but we're going to look for it in the range that goes from the middle index plus 1. We've already looked at the middle index, so we don't need to look at it again. And we're going to go all the way up to, but not including the search range's end that we had so far. Or maybe we should be including it. We'll find out. The search range dot upper bound. We may or may not need to actually be including this. We'll run it through a couple of edge cases and make sure that we can find it. But we'll do that as a debugging thing. So this, delete here. So this is our recursive call. We no longer need anything at the bottom because all of our paths return a bool. Yeah, go ahead. Yeah, I think so. All right, let's do that. I didn't before, but I think I was wrong. Can't make a closed range into a range. This is interesting. Well, no, the syntax for it's this, but it's it can't do that type conversion on its own. We could add 1 to the upper bound, but that doesn't necessarily seem like what we want to do, because maybe we've already looked there, right? Let's try it like this and then see if we get those off by 1 errors, but we will look at those edge cases. So I'm also curious to know. There are a lot of edge cases with these kind of algorithms. Okay, so that is our search algorithm. So let's go ahead and actually do that now. We're going to run it through some of those edge cases and see if we can find what we're looking for here. So we've got a little bit of boilerplate here, which is building our range. But the code from this is actually pretty quick and to the point. We say, if our lower bound is bigger than or equal to our upper bound, we've looked at everything and we didn't find it. Return false. Otherwise, get the middle index. If the target is at the value of the middle index of the array, return true. If the target is less than whatever that value is, then look in only the half of the array up to the middle index. And if the target is bigger than that, then look in the other half. And keep repeating this, as a recursive call, until you've either found it, return true, or you've gone and seen that there isn't that element. So let's run it through a couple test cases to see whether or not this does what it's supposed to. So let's build an array. Let's just make an array of numbers. And then let's run our binary search. Now, notice the whole reason we went through this array song and dance thing was if we didn't make that thing optional, we would have had to pass in the range of the array, and that's like a weird thing to do, because we give it the array. Like, you, as the function, should know what to do with this array. We shouldn't need to supply that. So we'll pass in the array, we'll pass in the target, let's say first of 8, try an easy one for it, and see what it can find, if anything. All right, it did find an 8, so that's good. Let's then check our upper bound and see if it finds our 10. It did find our 10, okay. So now let's figure out why it actually found our 10, shall we? Because our hypothesis before was, hey, if we're going up to but not including the upper bound, doesn't that mean that we're not going to include the 10? But we still ended up finding it. So something happened. Let's do a little bit of investigating and see if we can figure out how it found that value. It is indeed a mystery, but one that we will solve. So one thing we can do, and this is very helpful with any of these search functions here, is once we have our range, let's print out the range that we're looking at. We are looking for target in search range. And now it's going to descriptively tell us what it's looking for. So it's telling us here that it's looking first in the range from 0 to 9, from 5 to 9, then from 8 to 9, and then it found it. I put it right before the base case, so it's going to run in every branch that we go for. I guess this 11 is kind of always going to be the same. But the interesting thing is the range here. First, we have 10 elements in this array. Is that actually true? 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, yeah, 0. This is the 0 up to and including 9 is the same as 0 up to and including 8. We looked for the 11. We said it wasn't there. So we found our, the value then. Let's go ahead and have it tell us that. Print the current middle value is r at middle index. It's good to have your functions talk to, let you know what's going on, especially for recursive ones. All right, so the first thing it looks at is 7. Then it says, oh, that was too small, so I'm going to go ahead and look instead at the range from here, starting at 5, so 0, 1, 2, 3, 4, 5, up to 5, 6, 7, 8. So we can see that this end index it picked was actually 9. Why is that? Because we started off our range with this r.end index, and end index is one past the end of the array. So this range here ended up building the range that I think we wanted in the first place. What's that? R.end index? Convention. The array's past the end position. That is, the position one greater than the last valid subscript argument. So presumably that's why we're still finding what we're looking for, even though we are not actually incrementing above that range there. So we're saying build a range that goes right here, right up to the end. It still seems like, I don't think. Okay, so this gives us here a range that goes up to 9 each time. It does seem like it would build a, yeah, search range upper bound is 9. That's why, basically. Because search range upper bound, I think, is not the less less than, is the less than rather than the . That's actually, so that's why that's working out for us here. This search range upper bound is that 9, and we actually want to build a closed range up to that 9. Does that make sense? So like this number here is 9, and we don't actually want to look at index 9 because that's off the end. So this number is 9 because this value here is going to give us 9. So we're always going to be building that same range. So we're going to still get to look at index 8 where our thing actually lives. Oh, the ... If we use a ... that would mean that we wanted to look at index 9. That doesn't actually exist. That wasn't why we got the error, but that's why we wouldn't want to do it. We got the error just from a Swift type thing. Yeah. Okay, so we are finding what we're looking for. Great. Let's do some runtime comparisons now and see how much more efficient is our binary search than the containment for big arrays. So the one thing we'll need to add is just for tracking, we're going to make a new property called number of operations, which is going to be an optional int that will give an initial value of 0. And when we call this function here, we're going to continue passing on, spreading this out a little bit. We're going to pass on that new number of operations. That's just incremented by 1. So this is just going to let us know how many times we looked at something. There's a lot of different ways we could know. Like I didn't have to do that before. It's okay. And this will just let us know where exactly how many operations we had to go through to find it. We do know from this, the print statement just tells us that as well. This is just another way of tracking it, so we can end up with a single printout that has it here. So then when we find it, I'm just nil coalescing, because if they give us nothing, then actually, there's no reason this has to be optional. All right, there's no reason this has to be optional. Sorry about that. Okay. So, great. Now when we find it in this return true, we'll do the same thing we did for this right here. We can say that we found our target in however many of operations. And if we didn't find it, we'll print that out, just so we can have that track working for us. Okay. If the search right before return false, I'm just printing we didn't find it, and right before the return true, I'm printing that we did find it. So now when we run our binary search on the small array, it's going to tell us we found it in 2 operations. Pretty quick. I guess we're starting at 0, which is a little bit disingenuous. So let's start at 1. Because the first time is really an operation. And then we can go ahead and remove our other print statement of what that range looks like if we wanted to. Okay. So this is kind of interesting for small arrays, right? We're like, okay, we can see what's going on. But we don't get into this kind of scale until we start getting a lot of elements, right? So let's build some big arrays and then run it through both of our searches and see what it does with it. How do we build some big arrays? There's a bunch of different ways we could use the array repeating, but we want to mix it up with a bunch of random numbers. So we're going to use this neat little constructor I found somewhere in Stack Overflow. We're going to go ahead and make an array that's built from a range here. This is basically just saying, do this 900 times. Take this range and map, where you don't care where the number was coming from, and just give me a random number in between, say, 0 and 1,000. So this is just building a big array of a bunch of random values. Now, it's true for what we're working with that it has to be a sorted array. So we're going to go ahead and sort this array. And we're also going to remove duplicates in the process, just because we don't want that cluttering up our algorithm. So we're going to do the following. We're going to take this array, turn it into a set, turn it back into an array. That removes duplicates and the order. And then we'll go ahead and sort it. Yeah? Oh, you're for 63? Yeah, it's functionally exactly the same, actually. Like this line here, we can write it that way instead. Oh, you're saying like to build it and sort it at the same time or something? Oh, that might be faster, but I don't really care about how we're building this because that's not part of our algorithm. Our algorithm just assumes that someone gave it a sorted array. If you're right, though, if we were asked to write a function that returns a sorted algorithm, we would be doing it slower right now because sorting, as we'll get to, is what's called linear arithmetic. It's better than linear, worse than quadratic. So the algorithm we're writing right now isn't actually that efficient. But we don't have to be writing an efficient algorithm right now for it. That's okay. It's a fun one, though. If you want to write a linear algorithm to do that, I welcome you to. Okay, so now we have our sorted array with a bunch of things in it. And now we can figure out how long does our contains take on this sorted array, looking for, I don't know, one of these other random integers. So each time this runs, it'll tell us that it found 851 in 517 operations. We'll run it again, and it'll tell us that it found some other number, or didn't find it. Now I found 917 in 531 operations. So on average, because it's a bunch of random stuff here, didn't find in 596 operations, and those are the duplicates removed. So on average, it's going to take a few hundred operations to be finding this here, right? Sometimes we get lucky and the random number we're looking for just is smaller, so it's closer to the beginning. But sometimes we get unlucky and it's not there at all, and we have to look at 600 plus elements to find it. So let's see what our binary search does in regard to this. Let's make this the target so that they're both looking for the same thing to make it fair. And we'll check our binary search of the sorted array looking for our target. And now we'll just have them talk to us about how long it took. So here, that's a lot of print statements. Let's get rid of those. And okay. So it tells us for our linear search here, it took 600 operations for it not to find it, because it wasn't there. Our binary search did it in 10 operations. That's like 60 times better. That's really good. That's a lot more efficient of an algorithm. And I'll go ahead and have these tell us who they are. So I'll just write it here. So we'll write, friends, this one first is a linear search, and then here is our binary search. So we can see the savings from our binary search here is that we are like 2 orders of magnitude times faster about finding it because we know how it's ordered. And as our array starts getting bigger, like instead of having only 1,000 items roughly, let's say that we have 10,000 items in our array. When we're running our linear search, chug along, there we go. It took 394 operations to find it, but we only took 9. Oh, because our number is still small here. Oh, because we have a lot of duplicates. So we should expand out our randomness here. Great. So it took 6,000 operations for our linear search to get through this because of our duplicates. It had to look at everything, right? Makes sense. Our binary search only had to look at 13 things in order to go through all 6,300. It didn't really need to look at all of them. It could be very smart about what it was looking at. And we can have it tell us those ranges. Let's put that back, actually. Let's have it tell us those ranges, and we can see the swaths that it's taking out of each time that it's looking. So here, we'll just go ahead and print the search range. So where our linear search algorithm is bound to having to look at everything one at a time, we can see our binary search here in 13 operations starts off from saying, we're looking at everything in the array, 0 to 6,361. Then says, oh, I'm looking for 8,000 whatever, blah, blah, blah. Like, I know that that's going to be in the second half, because whatever it found in the middle was smaller than it. So we chop off half of our entire array. And we keep chopping off. And by the time we chop off here and get to a range that's only comprised of 1 element, we've made 13 operations in 13 cuts. So we're able to grow, as the array keeps growing bigger and bigger, we still don't need to spend that much more time looking through it. Yeah?
So with data containers,
Yes.
you usually be able to find examples of how they're actually used.
Yeah.
Is there something like that for...
That is a great question. Let me introduce, you all love Git, right? Let me introduce you to the wonderful world of Git bisect. Git bisect says, use binary search to find a commit that introduced a bug. I've used this before, it's good fun when it works. The idea of Git bisect is, let's say that you're working on a project. It's a big project. You have dozens of different people making commits and changes. Your product team reports a bug. When you click on a button, something doesn't appear that should appear. They report this bug because, not just QA tested, but because a user reported it. They say, we have no idea how long this has been to report. And your job as a developer is to find who introduced this bug, because it used to be working correctly, and fix it. Your 2 options are either ignore the past and just try to fix it, which sometimes is a good idea. Your other option is, what if I could find exactly when it was broken? How can you do that? Using git bisect, what you do is you say, this commit right now is bad. Git bisect's super fun. So the commit right now is bad. So it says basically right now at the beginning of time, or the end of time, whatever, this is a bad commit right here. This commit hash. And this is commit hash 3h2, whatever. And then you say, but back here a month ago, I'd commit hash, 2hfgj, whatever. This one was good. In the middle, there are a bunch of things. There's hundreds and hundreds of these that are all question marks. If the only way that you had was to find out whether or not this thing was introduced was, well, this one's good, I'm going to start at the beginning and go through every commit one at a time until I get back up to me. It might take you 200 checkouts to find what you're looking for. Git bisect says, I'm going to be very clever, and what you're trying to do right now is a binary search. You have a bunch of time-stamped commits, right? The thing that they're sorted by is the time of the commit that they were made. This one is good, this one is bad. I'm going to go ahead and pick one in the middle and say, is this one good or bad? And it asks you, and if you say it's bad, then it says, well, if this one's bad, then I still need to keep going back in time, and I'm going to split the difference again and run through that same process. If this one's good, then I'm going to split the difference the other way and run through that.
This works because once it's bad.
Yeah, I mean, if that happens, then you're kind of out of luck, right? You're right. This would only work if a bug was introduced and then not reverted and changed again or whatever. You are totally out of luck if that happens. This is assuming you can identify good and bad and that there was a single transition point that switched things. Yeah. Oh, it would work all the time. The example that it was citing is, let's imagine that you had a button, you click on it, something's supposed to pop up. Let's imagine that this one's good, this one's bad, then someone fixed it, and then someone broke it a different way, and then someone fixed it, and then someone broke it a different way. Now you're out. It does work for most systems. It should work. It should work though. As long as you don't have that kind of stuff happening. And you can actually find this. If you want to mess around in one of your own repos, and just see what this process looks like. There's, where am I here? If you just run git bisect, tells you, oh, at the top level, fine. Git bisect. It starts asking you hey, here's how you do git bisect. You say, tell me the good commit, the bad commit, and then I'll start doing a binary search for you. And I think, let's see, git log. Let's make up that this one's good, and that this one's bad, and this one's good or something. So let's do, is that the syntax? Git bisect good is this, no. Which one I say was good? First one?
Yeah.
No, is this the most recent one? Hang on. Let's run this again. 322E. Okay, that's the bad one then. So let's go ahead back to git bisect and say that the good one is here and the bad one is here. Git bisect, I haven't done this for a while. Start. Whatever. There's some syntax that makes this work. Oh, I'm already on the. I don't know why that's being funky. Yeah. Good point. Anyhow, bisect works. You can look on Stack Overflow. Just link to that Stack Overflow. Git bisect. And this is a real life example of like how to actually use git bisect to do what you're looking for. And each time it tells you, bisecting, 2 revisions left to test after this, roughly 2 steps. The reason it knows how many steps are left is because it knows how many more divisions it should be. So bisect is a really cool tool. You might not see much use of it for projects that you're making now. It's really great if you're working on like a code base that's been around for a year or something's been introduced 3 months ago and you want to be able to check it out. So that is a practical application of binary search. It does happen in a lot of like other more low-level things, but this is one place it comes up. All right, let's head back to the code. Great, another bit. Oh, the linear one? Yeah. So our contain, I'll slide all this out. Our contains function is our just straightforward linear one where we're just going through one at a time, seeing if it's there, seeing if it's not. Yeah.
So here we're starting off with 0 for number of operations, and our binary search is started off with 1.
Because in our binary search one, so in the order here, we start at 0, then the first thing that we do is we look at something and then increment. For our binary search, we start at 1 because we look at something before we increment, right? So here we end up incrementing the number of operations here, so we started off at 1. If we want to do 0, we could. We could start it off at 0 here, and instead we increment the number of operations when we're looking at something earlier, which would be like, I guess, here. It's because the looking at something is like this code right here is the thing that actually looks at something. Does that make sense? So like the 1 counts looking at this the first time, and then we increment it once more. You're right, though that might be off by 1, like in that, like at the end case maybe. But because we're looking at something 5,690 times, it doesn't really matter. Hmm? Yeah, the binary search has those applications for like git bisect and like other occasionally like clever ways that you see it being implemented. For the most part, again, as with everything that we learned in here, you should probably not be writing binary search algorithms for things that you're writing, unless you have a lot of data and it happens to be sorted, in which case go for it. Yeah.
Alex and I have the same thing for the function.
Okay.
Whenever we do linear search, it's always looking at an operation.
No matter how many things you have in the array.
Correct. Both of us.
What's your this is the code that you're running through? Is this how you're building your array? Or are you building it differently? Are you building an array that only has 9 things in it? Probably. Oh yeah, I just upped it. Yeah. You can Slack it out and we can debug it if you like. You can put it on the channel. Hmm? Who are you? 6'1"? Yeah, you want to Slack to the channel? I can put it up and then we can figure it out. And I'll talk about the lab briefly. What's that? Oh, sure. Was that what was there? Very nice, I know. It was very cold though. That was yesterday. Yeah. I was prepared. I don't know about you. I think the new people will get told that. You figured it out? Alright, sounds good. Okay, so this is a gist of binary search. Again, it has occasional of those uses for like git bisect and other cool places you see it show up. For the most part, it doesn't come up unless you have like very specific problems. Okay, so with that, the lab you can find linked to from Canvas. What's that? Oh, I'll do that right now. How about right now? It's happening. Right now, attach, create new, code, snippet, Swift. There we go. I think that also has my commented out notes from before if you want to see it. think it's the same. Okay, so at the lesson stuff, you have binary search problems. So these here are having you run through first just writing binary search again, doing it iteratively instead. We did it recursively. Anything you can do recursively, you can do iteratively. So that's more of a just like fundamental algorithm writing stuff. And then a couple extra problems I found that are asking you to use binary search in a couple more innovative ways. And these are all things that I just pulled from websites that purport to ask things that you might find in interviews. So it's good to be practicing with them now. There are associated tests with this as well. The tests should work, but as always, let me know if anything is broken there or doesn't make sense, and then I can go ahead and correct it. Questions? Yes? Yeah. The good news is you don't actually have to. Very few people actually like come up with these. Like when we're doing this sorting algorithms as well, like you'll see that some of them are really clever, like when you get what they're doing. Like for quick sort is a way of sorting that's like take something in the middle and then like do a chop in half, like the left chop to the right, and then like keep running that until you get down to single elements and then combine them and then build it back up. And you look at it and you're like, wow, that's really smart. So like people win like awards for making this up. Like it is not at all the kind of thing that like as a developer you should be able to just like go from nothing and then just come up with binary search. Like that's a reasonable thing to do, right? Really, really smart people can do that. Like you could do that if you just spent a lot. Like if, instead of spending time doing things like learning how to build iOS applications, there are people who spend all of their time just figuring out how do I build more efficient algorithms. And those people are the people that end up making and coming up with new things like this. But yeah, generally like people have like won awards for making stuff all like this. Not at all like coming up with the idea of it is not an expected developer thing. Being able to implement it definitely is. Yeah. So don't worry about the like, well, it's like I don't think I can come up with that. Like no, like 0.1% of like people come up with stuff like this. Like we'll see a lot of stuff that's like you're like, I guess that's cool, just learning this, but like it seems very clever. Like your job isn't to make those up, unless you want it to be, in which case you get a job doing some like fancy algorithm stuff. Yeah.
So since these are like interview questions,
Mm-hmm.
is the expectation in an interview for you to be able to execute it correctly, or do they just want to see that you work towards it?
That's a great question. So it depends on the interview. There's like two or three different species of interviewing that you'll get. One of them, they'll just expect that you know that. So like at the lowest level, I think everyone would expect that you've heard of binary search, that you know it's faster than looking at everything one at a time, and maybe that you can remember that that's called logarithmic, because you're chopping about half actually a lot. And a lot of people are totally content with that as interviewers. Other people, generally at more established or bigger companies, would do things like the questions I have in the lab would just ask you that. Be like, hey, write a binary search for matrices instead. And like, do you know how binary search works? But it says, but write it a little bit differently. Like write it using these tweaks to it that show that you understand A, you can just write it from scratch on your own, but B, that you're able to write and change it because you know what's going on with it. So those are two different like tiers of interviews that you get. So at a lowest level, you should definitely be prepared to like know what it is, know how long it takes, know roughly like if you can explain like this picture and just kind of like understand that, you're in good shape with a lot of interviewers. But some are going to want you to build it. And for that, we're practicing because we want to make sure you're ready. Yeah.
Can you do one question together?
The first one is to build this. So yes. Oh man, I haven't done that yet. It looked hard. I said it looked hard. We want to try number 3 out? We can try number 3 out. All right, let's try number 3 out. Let's go ahead and get the lab done. If you'd like to just start and stuff on, you're welcome to, but we'll go ahead and give that a shot collaboratively. I have this lab somewhere, I think. This is a lab, right? Labs suit for binary search lab. Get rid of that. Okay. So we're going to give number 3 a shot from the lab and see what happens. Now, the tests are not actually benchmarking you to time, so you can cheat, but you know. All right, so number 3. Find if a value is contained in a matrix of dimensions m by n. This matrix has the following properties. Integers in each row are sorted left to right. First integer on each row is greater than or equal to the last integer of the previous row. First thing you should do in these is like, what does that look like? What is that supposed to mean? Take a look at the test file. And the test file says, get rid of that hotkey, still upset. Number 3, binary search, recursive binary search, matrix contains. That's going to be hard to look at in presentation mode, that's okay. All right, so these are what our test cases look like here, right? Not up a bit, I think. All right. So we have arrays that look something like this. Each row is ordered from left to right, and the number on the next row is always bigger than the last number up on the previous row. So what is this process going to look like? We can think of this as doing 2 different binary searches. The first binary search that we need to do is find out what row to look at, and then once we're on a row, we just need to find that element. Does that make sense conceptually? So if let's say we're looking for the number, it's like, I don't know, better one, like 21 or something, right? We can look and say, okay, first we need to figure out what is it in between the 2 rows, right? What's the next row that it could be on just at all? So we start off, we say, okay, we look at, we do a binary search to figure out what row should it be on. So we say, we make an array, I think, out of 1, 10, and 23. And then we say, well, the number that we're looking for, if it's, say, 21, we know that 21 can't be on 23's row because it starts 1 higher than that. So it should be on the row that's right before that. Right? Now, we have to do a binary search to get there. Because we want to find out what 2 rows it's in between, and then pick them. Right? So we say, we're going to get the index that's 1 before or in the middle of like where it's going to be. Then once we say, okay, that 21, if it's here, it's in between these 2, so we're going to pick this one. Now we go to this row, and we look for 21 and do a binary search on that. Does that make sense conceptually? So first we go down the columns, and we figure out what row it should be on. Then, once we know what row it's on, we just look inside that row for it. We can do this iteratively, by just going through one at a time. But the problem says that we want to have a good runtime, so we're going to try to do it the most efficient way possible. Yeah, iteratively could just be, well, we could do it quadratically, where we just look at everything, right? We can do a lot better than quadratic for this, though, because we don't need to, like, let's imagine it's 100 by 100 or something, right? And the number we're looking for is 1 billion. Like, that might just be in the last row, and we just didn't need to waste any time looking at all the individual nested elements. Okay, so let's give this one a shot, shall we? All right, so we have a 2-dimensional array. The first thing that we need to do is run a binary search on like these indices here. So we're going to implement kind of a double binary search kind of thing. So we're going to first find the correct find the correct row that we're supposed to be looking for. So we know the value we're looking for. We have the array. Let's try to do this iteratively, I suppose, and just keep track of some indices. So let's have our let min index is equal to 0. Let max index is equal to the number of rows. We could do this with ranges as well. So this is saying we're going to start looking at, these are row indices right now. Should make that more clear. Min row index and max row index. So now what we want to do is look through all the first numbers in those and figure out which two is it in between. Like where roughly would we find our thing if we were able to find it. So the way we search for that is we check and see. We need a current index, or this should be, I guess, you can make these variables. Yeah.
Is there a way that now in this case is how you know
Mm-hmm. Yeah. So we're not actually looking into the.
in the array?
Yeah, we're just trying to find what row to be looking at. So the r.count is telling us that you have 1, 2, 3, 4, 5 different rows. So we're going to start looking from index 0 to index 4. So that's why we care about the count of the array of arrays, because that's the size of our matrix. So now we want to say, let's pick the middle index. I guess while min row index is less than max row index, do the following. Kind of, there's a little bit of how you do it iteratively as well. Let's get the middle index, and that's going to be equal to the min row index plus the max row index over 2. So that's going to be the middle row index of the current things that we're looking at. And now we're going to take that middle row index, and we're going to check the value there. If the middle row index, if the array at the middle row index at 0, that first element, is equal to the value, we got super lucky, and we can just return true. We actually don't expect this to happen a lot, right? This means that we did a search through it, and we actually just found straight out the number we're looking for. It happened to be at the beginning of the row. That was good, so we just returned true because we found it. If that didn't happen, if instead, if the value is less than the r at middle row index at 0, then what we can do is we want to go ahead and say, well, the value we were looking for was less than that middle row index thing. So in this, so in this matrix that we have here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, say something like this. So in this, let's say we're looking for 7 or something. We say, okay, we looked at the middle, or in this case we have the values. Let's say we're looking for 2. We looked at 5, because that was the middle row, the first thing in the middle row. We're looking for 2. We said, oh, this 5 here is bigger than the thing we're looking for. The target is smaller than that, so we want to then say that the max row index is going to be 1 less than whatever this was. Right? We're going to restrict the scope of what we're looking for. Instead of going from, we're looking from 0 to 2. Instead of looking from 0 to 2, we're just going to look at this row only. If we had more rows, which would make it more interesting, say 13, 14, 15, 16, 17, 18, 19, 20. So say we're looking for 4. We pick this, and we say, this isn't right, 4 is smaller. We're going to restrict our max index to be this one right here. Right? Because we know that the max row index for where 4 could be has to be less than the middle one. So we're going to take our max row index, and we're going to set it equal to 1 smaller than the middle row index. If the opposite is true, and if the value is bigger than the array at the middle row index, this first thing, which I don't need to write. I can delete that because that's just more explicit than we can do, that's fine. Instead, we're in the other case where let's say that our original range of was from here, start, and or what I call that, min row. This is min row. Right? And this is max row. This is the middle index. If we say we're looking for 14, 14 we know we're not going to find in any of these 3 rows. So we're going to up the min row index to be right here. And now those are the 2 that we're going to look at. this array was a lot bigger, then we'd still have a bunch more things that we need to be looking at. So here we're going to take the minimum row index and set it equal to the middle row index plus 1? Yeah. Plus 1. Yeah.
How do you increment or decrease by 1 as opposed to using binary search and different middle?
We are, so the decreasing by 1 is saying, like, we have 5 rows right now, so we're saying that, again, more rows, hang on, we need more rows. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's say now our middle is, so now our middle is here, right? If we're looking for, this is our min, that's our min still. This is our max. If we're looking for, let's say 24, we look here and say, hey, 24 is bigger than this value, right? So we want to look now in this range, right? We don't care about anything up here if we're looking for 24. So what we say is, how do we now specify that the minimum range is at the top of this zone and the maximum range is still at the bottom? We say, oh, just go 1 down under the middle range, and this will now give us our new minimum range. So that incrementing by 1 only looks like we're doing it linearly if we have a small number of elements. If you imagine that this here instead had like 50 rows, then it's much more clear that this range might include 20 or 30 different like rows on it. It's a good question now. Okay, so we end up with this row index, minimum row index here. And after this runs, one of two things is true once we're done with this while loop. Either we've returned true, nice, or our minimum row index is no longer smaller than our maximum row index. They've overlapped. If that happens, then we found the row, I believe, that we want to be looking at. Let's double check to see if that's true. How does this end? Let's say that we're looking for 24. We then check this range. We then say, okay, we're looking for 24. It's bigger than this, so we're going to pick the range. So now our minimum range goes to be the same as this one here, right? And so they overlap and they're the same. We can then check to see if the number that we're, actually, I'm not sure if we need to, no. Yeah, I think then we just go 1 smaller than that, and I think it has to be on that row, unless I'm missing an edge case. Like, if we, let's say that instead it happened so that this was the min, and this was the max, like if there's an even number. So if we're looking here and here, because the min could be the same as the middle, if there's only 2 rows, I think. Yeah, for an integer division. So if this is the min and this is the max, and we're looking for 24, we'll look here and here. This will be the middle. We'll say 24 is going to be, actually, what do we say? We say this is the middle, 24, we go up 1, and then we still want to go down 1. So I think this will work, but we'll check our edge cases. So the row that we ended up on is in fact the one that we want to be looking at for that middle index. The middle row index is going to correspond to the value that we're interested in. Again, that's probably true, but we can debug some edge cases if and when we need to. So either when we exit here, we've returned true because we found it, or our new min row index, which is the same as max row index, I think they have to be equal, reflects the actual value that we want. So I'm just going to rename that. So like let current row is equal to min row. And I think these are the same at this point, but we can run it through a bunch of test cases and find out. Okay, so now what did we end up with? We ended up with the current row that we're looking for. So we can actually find the, let R actually, yeah. We can now define our new array. So this is the subarray, or target array. I don't know. Let's call it the target array is going to be equal to the R at the min row index. this array that we pinpointed here is the place where we'll either find it or not find it, and it wouldn't be anywhere else. A bold plan, we'll see this through. So, once we found the array that we're looking for, now we need to binary search in this array. Now, we could write that again, or we could be lazy and copy this into the other one. Because we actually have a, sure. Great, now we have binary search. You would have, for 1 or 2, you would have written this anyways as binary search. So I'm just going to use this binary search. Why not? Binary search is binary search. Now we have an array. The whole point of writing code is that we can reuse it. So we can then return whether or not, which one's mine? Ooh. Hang on, call this Ben binary search. Thank you. I will also need to update these names here. So I'm just using this method here, and it just happened to have the same name as one we had written already. So let's take this Ben binary search. Contains. Great. So now we can return whether Ben binary search of this target array, looking for the target, which we call value here, is contained. And if all has gone well, this will actually run through our test cases and tell us whether or not we found the value. If it hasn't, then we'll have some fun debugging. It's a win-win. Okay, so this is problem 3. So let's go ahead and run that test case and see if we fail somewhere interesting. Nice, nice, nice. So the tests are telling, so either the tests are poorly written or we pass them, maybe. But the tests don't build giant arrays, but this is a very generically written algorithm. Like, we didn't care if there were 4 arrays. This would work with a million different rows in the array, and it did pass all of the test cases we had written. So conceptually, what we're doing in this algorithm is we are finding the row. That was all the first bits we did here, is find what row to look at. Then once we found the row, or either we found the value, or we found one past the row, and then just went back one. Then we looked inside and did a binary search inside that array to see if it had the value we were looking for.
Where did you place them binary search?
As put at the top.
Or did you, oh, so you didn't put it in the first one?
Oh, no. Yeah. It says do not use recursion there. I know. That's fine. I mean, we basically just wrote this here, right? This right here that we just wrote, this is a binary search without using recursion.
What we use for right now, that could be that on the
The index stuff? Yeah.
The one you use it now.
That's number 3.
Not
Oh, the binary search one? Yeah, that's number 2. Yeah. Yeah. We did number 2 in class, basically.
and we can go into
Kind of. This is part of it. This is number 3 that we just did. This includes part of what you might call number 1. The iterative binary search.
we're in number 1.
Oh, no, because it's supposed to run in logarithmic time. Contain still runs at linear time, right? So the goal of binary search is, if you're looking at everything, you're not doing a binary search. To do a binary search, you have to take advantage of the fact that the list is sorted, and not look at everything, but only look at the middle. Figure out what's half we're looking at, and look at the middle again. If you're not doing that, it's not a binary search. Yeah. Binary search means that binary is like 0 or 1 kind of stuff. It means you're splitting 2 every time. Yeah, it has to have that kind of structure. So that's like what we do here, right? We do that same thing where each time we're bumping up the middle row. So like here we're looking at all of these rows. Then we find the middle and chop off half of them. Now we're only looking at half. So that counts as binary search. Good old binary search. Right. So I was saying the runtime of this, if the matrix of dimensions m by n we have to do 2 binary searches. This is a binary search, and this is a binary search. One of the binary searches is dependent on the size, the height of the matrix, and the other is dependent on the width. This binary search, if we're saying it's n by m, where this is n and this is m, this binary search here is log base 2 of m, and this binary search is log base 2 of n. So the runtime for our algorithm would be described as log of m plus log of n for what the runtime is. Because we have 2 things that we're doing in sequence, where we don't have them nested. And I think this is even from a website, I think that you might be able to submit this to. Not 100% sure. Okay, questions on this? Yeah. You can add, if you need to add more parameters, you can. The way to make it work with the tests is you can just make them optional with initial values, or just with initial values. You can also do it iteratively, but you can use helper functions. You can do whatever. You can do whatever you like. The tests are just there so that you know if it's working or not. Yeah. Okay. So this is the lab. There's a few more good ones on it. Focus on the first 2 that you feel like you understand what binary search is doing and that you feel like you know what it's doing both iteratively and recursively, and then you can give some of the others a shot. I will store the video from this. You should already have the notes here, and I suppose I will also Slack out this file so that you have it as well. Thank you all. Yes.
Pasted in my binary search from the notes we took earlier.
Yep.
And it says there's an extra range argument in this call, but I have that in my arguments here.
You see this is Sunny binary search,
Oh.
and this is just binary search. Yeah, that was a little bit confusing. I made the same mistake before.